Okay, in this unit, we'll talk about another approach to proving implications, which are proofs by contradiction. Let me start out by something that looks a little strange, but continues from the previous unit about logical inferences. Okay, so consider the following inference rule. Not P implies false is the assumption, and P is the conclusion. Okay, let me first claim that this is indeed a sound inference rule. So we'll go ahead and draw out the truth table here. And so just to test yourself, what is it that you need to see in this truth table to convince yourself this is sound? Okay, so it's a bit tricky because it's done backwards this time. What you need to see is that for every row where the assumption is true, in this case the top row, the conclusion, which is just P, is also true. Okay, and in this case, indeed, we passed the test, and this is okay. So this is a sound inference rule. Okay, so take a look back at this again. This maybe looks a bit arbitrary, but it turns out it is a very interesting and very useful rule. If you could put like dramatic music. Da-da-dum. And this exactly leads way to another approach of proof, proving by contradiction. The idea is, suppose I want to prove some statement P. Okay, and this is now a general statement. So before we talked about implications, we talked about if and only if. Now P is whatever. It's just some statement. Okay? And what we showed on the previous slide means that to prove the proposition P, it suffices to prove that not P implies false. Okay, so what does this mean? What does the proof by contradiction look like? The first thing you do is to write, assume by way of contradiction, not P. Okay, so this is this first part here. And now what do I want to do? Okay, so I want to prove not P implies false. I need to again take some sequence of logical steps whose conclusion is false. What does that mean? I need to somehow take logical steps and find a contradiction. Okay? So what does that mean? Because once I have a contradiction, that means that false follows from this. So this looks a little strange, I imagine. I think that it can be very helpful to go through and see some examples. Consider the following claim. Let x be an integer and suppose that x squared is even. That is, that x squared is equal to 2 times y for some integer y. Then x is even. Okay, so let's take a look here on the board. Now suppose I want to prove this by contradiction. So remember, what is the first thing to try to say? First thing was assume, for contradiction, that not P holds. That is the negation of what we're trying to prove. So here what is this negation? Assume for contradiction that x squared is even, but x is odd. Okay? This here is not P. Okay, and remember, so we've written this, and now the goal is to somehow take logical steps until we reach some contradiction. So let's continue with this. And let's start with the fact that x squared is even. Okay, so now remember, we need to take a step of logical sequences until we reach some contradiction. And let's start this out by using the fact that x is odd. Since x is odd, it can be expressed as some 2 times y plus 1. Okay? For some y that's an integer. All right? Now let's take a look and see what does this imply about x squared. This means that x squared is equal to 2y plus 1 squared, which is equal to 4y squared plus 4y plus 1. Okay, so this is some expression, sure, that's great. But what do you notice about this thing? This is equal to 2 times some integer, in fact 2y squared plus 2y plus 1. This implies that x squared is also odd. Okay, because of this plus 1. And what does that mean? I now have x squared is odd here, but I assumed that x squared was even. This is a contradiction. This contradicts that x squared was assumed to be even. Okay? Thus, it must be that if x squared is even, then x is also even. Okay? So this is the contradiction, and therefore we could conclude, since we showed not p implies false, that therefore p must hold. Let's do another example. Here the theorem is square root 2 as a number is irrational. Okay, so maybe actually you guys will or have recently seen this in calculus. I want to prove it in any case, because this is a really great example where proof by contradiction can be very helpful. Okay, so let's do the proof here. Well, how do I start a proof by contradiction? Suppose not. Suppose for contradiction that square root 2 is not irrational. That is, square root 2 is rational. Okay? What does that mean? This means that it can be expressed as square root 2 equals sum a over b for some a, b that are integers with b not equal to 0. Okay. Now, I'm going to do something. It's going to seem a little odd, but we'll see where it comes in. Without loss of generality, I'm going to assume that a and b share no common factors. Okay, so for example, they cannot both be divisible by 2 or divisible by 3 or anything of that form. And why is this without loss of generality? Because suppose that they did have a common factor. Now I've got a divided by b. I can just cancel out that factor and come up with a new a prime and b prime, where a prime divided by b prime is equal to a divided by b, but now that factor is removed. Okay, so I'm assuming that a and b do not have common factors. Now let's go back to this. So square root 2 is equal to a over b. This implies, okay, that 2 is equal to a squared over b squared. Okay, so this is coming, just to write this additional step, squared, which is equal to a squared over b squared. Okay, which implies, just multiplying this over here, that 2b squared is equal to a squared. Okay. All right, so what does this mean? This means, in particular, whatever this a squared is equal to 2 times some integer. So a squared is even. Okay, here I've got this 2 times b squared. All right, well, if you recall, just moments ago, we proved something that in the previous claim, we proved that if a squared is even, then it must be that a is even as well. Okay, so from the previous claim, this implies that a is even as well. Okay, this means that A can be expressed as some 2 times x, let's say, for some integer x. Okay, now let's go back to the expression that we had before. So I know 2b squared equals a squared from before. Okay, and this is equal to 2x squared, plugging in what we just had, which is equal to 4x squared. Okay, so now what do I have? I've got 2b squared is equal to 4x squared. Cancel out one of the 2's, and I get that b squared is equal to 2x squared. Okay, interesting. What else do you notice about this? In particular, this means b squared is even. Okay, I've got this too. Good. But now, again from the previous claim, if b squared is even, this means necessarily b is even as well. So this is the second time we're using the previous claim. Little did you know it was actually going to be quite useful for us. Okay, but now pause, because I claim we've reached a contradiction. What is the contradiction? It's a little bit strange, but take a look here. B is even, we just proved it. A is even as well, but we assumed that A and B shared no common factors. And this is a contradiction, because A and B necessarily must share the common factor too. This is a contradiction. Okay, and what does that mean? Once you've reached the contradiction, you can conclude what the statement P was. And remember, going back to this, we started out with assume for contradiction that not square root 2 irrational. So we can conclude, I'm upgrading my thus to a hence. It must be that square root 2 is irrational. Okay, and that concludes the proof. Okay, so summing up, what are the proof methods that we've seen so far? From last week, we saw a couple different approaches. First of all, for proving implication, there is the just do it and the contrapositive. For proving if and only if, we saw a useful method for proving each direction separately. And we also saw some cases where you can prove a statement by comparing truth tables. For example, suppose you need to prove that 2 propositions are logically equivalent. You can show that they have the same. And today we saw a sort of generalization. Actually, the case of contrapositive you can view as a special case of this new broader method, which is proof by contradiction, where you start by assuming the negation of the thing that you're trying to prove, and ultimately reaching some contradiction. And just to kind of emphasize, this contradiction can come from wherever. In fact, we saw examples where it was contradicting this line together with this line with that line. But once you reach the contradiction, you're done. All right, so just a reminder to take a look and do the quiz before going to the next unit.